Our last talk for this session is about IMAP spacecraft and instruments in virtual reality, and we have Ian Hughes and Jake Strang presenting. So Ian is a senior software engineer at APL in the Space Exploration Sector Ground Systems Group. He's a VR developer for the IMAP VR project, and he's interested in developing XR applications to support the space mission systems engineering lifecycle. He's previously given talks at XR Symposia on lunar avatar and spacecraft harness fabrication in XR. Jake is a senior software engineer in the Space Research Analysis and Applications Group at APL. He primarily works on test and control of scientific instruments and development of mission science operations centers. Jake is interested in applying VR to science operations and analysis, and he contributed as a developer on the IMAP VR project. Away we go.
I'm Ian, this is Jake, just to make sure you can tell us apart. So I'll start with telling you a little bit about the mission as IMAP. So IMAP is a space probe, a NASA space probe that's being sent to the L1 Lagrange point. So it's basically going to orbit between the Earth and the Sun. This little animation here is kind of showing what it's doing. It's under development right now by APL as the primary spacecraft builder, and then the Princeton University is the principal investigator of the science team. And its job is going to be to study the atmosphere of our star. So you know, it's going to be measuring energetic particles and their interaction between the interstellar medium and the solar wind. There's been other missions like this, so this is kind of a predecessor to some later missions, which we'll talk about in a bit, because the data that's shown in the animation there is actually from the predecessor mission. So what is IMAP VR then? So we made a virtual reality application to basically immerse you into the IMAP spacecraft after it launches in its operational environment, and then also get an idea of what the kind of instruments that it has, and then finally we show an animation that actually gives you a feel for how it's going to collect the data. So it's primarily an education and outreach application right now, because IMAP hasn't launched, so there's no digital twinning going on yet, but it's just kind of to show you the instruments and its data. So first we have ability for you to take a look at the instrument models up close and all their glorious detail, and it's kind of like in a museum exhibit that lets you reach out and touch the instruments, and then you get a little pop-up that gives you a description about the instruments. Secondly, we're immersing you in the actual environment where the spacecraft is going to be after it gets there. This is the L1 Lagrange point. So if you're not familiar, with those of you who don't know what that is, this is the point in space of gravitational equilibrium between two masses. The L1 point, so there's 5 of them, L1 through 5. L1 point is the one that is in between the two masses. So for the Earth and the Sun, the two big masses that I'm talking about, the L1 point sits between the Earth and the Sun all the time. So as the Earth goes around the Sun, the L1 point always stays fixed at that point. There's nothing there, it's an imaginary point, but because of this gravitational equilibrium, you can actually have a spacecraft orbit that point. So the IMAP will hang out there. And just to give you an example, the JWST, the James Webb Space Telescope, is currently at L2, which is behind the Earth. So it's orbiting that point. So it gives you an idea that we do this all the time. We send spacecraft here. So we immerse you in this environment. So when you stand there, you can always see the sun. You look on the solar panel side and you see the sun. You can see that top picture. And then when you look behind the spacecraft, you see the Earth. And this point is actually much, much closer to the Earth than it is the sun, so you can still see the Earth. And the angular size of the Earth in our environment is correct. And then the last thing we have is an animation that kind of gives you a connection between the type of data that IMAP is going to collect and the instruments. So we have an inverted sphere that's kind of surrounding you, so it's a dome around the user, and then we can paint data on that dome, and we show the field of view of the instruments. So that's what that red cone is that's shooting out. It's coming out from one of the instruments, and then as the IMAP spacecraft spins and orbits, it will paint data on the heliosphere and show you. And this is counts of energetic particles at that point in the interstellar medium. So right now, like I said, it's an education outreach program, but we obviously have what future use is. We're hoping that we'll actually be able to turn it into a real tool that let you visualize the actual scientific data, as well as if we actually hook it up to the real spacecraft from litometry, we would get a digital twin. So there's lots of future applications. A little bit of our technology here that we're using. So to start with, we have real CAD of the spacecraft. So we have taken our actual CAD and we have converted it into ready for XR. So we use Pixie Studios to do that. That's an application, a third-party application that lets you basically decimate an actual CAD model and turn it into something ready for XR. So first we go through that initial step and then bring it into Unity. Actually, we also use NASA Mixed Reality Exploration Toolkit that Tom just talked about, Merit. So we're actually building that upon Merit, and we're using that as our basis. The version of Merit that we're using uses Unity HDRP. So obviously this is a Unity application, but we're using the high definition render pipeline. And the reason why I want to mention that is because it allows us to get a very high fidelity environment that looks really good, especially with the lighting. You know, Blake talking about that this morning, you can really get some good lighting effects from the high definition render pipeline, which lets you see the sun kind of glinting off the solar panels, makes it look really good, and lots of texturing going on there. Secondly, we have a simple model of the solar system, as I said. We have the sun and the earth and the stars, and you can see all of that. And I'll talk a little bit about how we did the art a little in a second. We don't have an artist on our team, it's just me and Jake that did this, so we were able to set that up between these two things with the model and the HDRP. And then finally, where I spent a lot of my time was on the custom shaders, and I'll talk about those in a moment. I had to basically set up that IBEX data, so there was a lot of effort that went into figuring out how to display the data on the inverted sphere as well as the field of view. So a little bit more about Merit, although you just heard half an hour talk about it, so I'm only spending a few minutes here. But the idea is that we have built this on top of Merit, although we're not using a lot of the features that Tom talked about yet. We're basically just using it as a way for us to load in the environment, and then it's obviously our VR locomotion and tools built in within Unity, so we can load our assets in. We don't support collaboration right now, but we want to, because obviously that's in Merit, but we don't quite have all the stuff that we built, like the custom shaders and stuff, working through the collaboration of Merit, although that's definitely on our short list. And then obviously there's GemSec, which Tom was also talking about in the previous talk, and that gives us that layer of being able to send and receive messages to a bus, or that's the middleware, and this can act as an architecture for mission operations. So APL does not use GemSec for mission operations here. We use L3 in control. IMAP will be the same. We will use L3 in control for our ground system. But GemSec has an adapter between L3 in control and GemSec. So we could use our software application in the future to actually get real telemetry from the spacecraft and show it in this application. So we can have it like a digital twin. So I like to point this out because it's just real easy for those of you who want to build applications. You don't need an artist all the time. Like I said, me and Jake are the only two developers on this team. We don't have an artist, so you just buy a $20 asset. You get all the textures you need. I always like to plug that, dump on the assets, or pull something down, and I have a beautiful texture of the sun and the earth to show in our application. So I started here. Okay, so then I'll just talk a little bit about the shaders that I built. So there's been two versions of this software that I made. When we first started out, we were like, okay, we really want to show the data on the heliosphere, but I don't want to show it all at once. You just click a button and then all the data shows up on this dome around you. So we actually wanted to show how the spacecraft collects the data. So I first created this shader that basically reveals the data in slices. So I should also probably point out, because I actually put it on this slide, IBEX data. So the data that's being shown on the heliosphere is actually real data from the Interstellar Boundary Explorer, which was a mission that launched in 2008. Also, principal investigator was Princeton University. So this is a predecessor to that mission that hasn't launched yet. So you can see how it's kind of all pixelated. You have these giant pixels on the color map of the energetic particle counts. IMAP is going to replace that data with something much higher resolution and probably more energy levels, all kinds of things. There's more instruments, better data. So, but we're using the real IBEX data here. So what you're looking at in that image is actual data from another spacecraft. And then I'm revealing it in slices over time. So this really gives you a connection between, and in fact, you can see the Earth in the back there. It's a little dot, but you can see it's moving to the left, or sorry, the data is moving to the right behind it, basically. So what's happening there is it's like time going forward very rapidly. So months are going by in a matter of seconds. So this is kind of showing you that as the spacecraft spins, it's collecting data over a long period of time and gives you that immersive experience. I know the 2D doesn't do it justice. You really go in there and you get a feel for what it's like how that connection to the instruments. Okay, so then I upgraded that to version 2, and now I'm like, well, what about actually showing it with a connection between the field of view of the actual instrument? Instead of just drawing these slices kind of randomly, what if we actually take the actual angle of field of view of the actual instrument that's currently collecting the data and then having that actually paint the data? So the second version of the shader started doing that, where I actually show the field of view, that's that red cone coming out, and then the data appears kind of where it's pointing, and it's kind of doing the same animation here. And then this was the other second shader I created, and this was a bit more complicated. I had to use signed distance fields in this case, and I'm actually drawing that cone, that field of view, without a mesh, because that's what signed distance fields do. So that's where basically ray marching from the camera, doing a calculation of whether you're actually looking at that cone or not, and then drawing that pixel. So there's a little bit more complicated of a shader that I had to create in order to draw this new mesh. And then it's actually using the same algorithm to also draw the texture to reveal the point on the inverted sphere at the point that it's looking. So it's checking whether the cone is intersecting with that sphere, and then drawing and turning on the pixel that's there. And I think that concludes me. Now I'm going to pass it over to Jake to tell us a little bit about the applications of this.
Is it working? Yeah, it's working. There we go. Couldn't tell first. Yeah, so Ian did a great job of covering what's going on in the application, the technology behind it. If you want the VR expert, Ian is probably the person to go to. But I figured I'd say a little bit extra about why we're doing this in VR, why we built it some of the ways we do, what we see as future applications of this in terms of not only the education and outreach part that we mentioned. This was initially built for a science team meeting to kind of demonstrate it and say, here's where we could do outreach, here's where we might go from here, but from there into, this is going to sound a lot like some of the things you heard from Merritt, going through the engineering stages of it, starting to do some visualization of the science data and some analysis of science data in VR, as well as moving on to the actual operation of a spacecraft. So Ian mentioned, is this going to play? Yeah, there we go. The ability to reach out and touch the instruments. So this is obviously great in terms of the ability to do outreach, that museum-style thing where you're going in, you're physically grabbing and rotating the spacecraft and touching the instruments and getting information about them. You can see immediately how that might be beneficial for engineering purposes too, being able to touch and make transparent the instruments, wireframe them, see the sizes, get a sense of scope, reach inside, see what you can do. So this is beneficial in terms of building towards that capability. Science visualization, obviously, you already saw what we're doing there, but why do we want to do that in VR? I'm probably preaching to the choir a little bit here since we're at an XR symposium, but it's a thing that I like to advocate for anytime we possibly can. We are inherently three-dimensional processing creatures. We're used to interpreting things that have spatial dimensions by seeing them in 3 dimensions. There's a lot of information you can get out of the data by understanding where it is spatially relative to each other that you can't on a flat 2-dimensional screen. So in this case, even just standing in the middle where the spacecraft is and seeing the heliosphere around you, where's the sun, where's the earth, where's the energy coming from, it gives you a different sense of that information and lets you kind of analyze that data and perhaps draw conclusions you might miss otherwise. So being able to import and visualize and interpret data in this environment is really beneficial to us. That connection between the instruments and the science is also helpful in a lot of ways, both in terms of interpreting after the fact and potentially in terms of deciding what we want to do next, which we'll see on the next slide as well. But that projected field of view that Ian built in, being able to see where is that actually connecting, how is it getting the data, where's the data coming from, where do we have overlap between the fields of views of our instruments, when did they each pass over a specific point in space at a given time. Being able to project that and actually see that helps us, especially as we move into things like other future applications for planning and operations. These are screenshots from some other projects, one being Lunar Avatar that Ian and I worked on as well. Another one is a more traditional 2-dimensional view of a planning tool. But that 3-dimensional field of view lets you see things like say we're planning in advance and we're not actually there yet, we can simulate, great, where are our instruments pointing? What are we going to see on the ground? Where have we collected data yet already, and where have we not? Let's load in a test command sequence and reorient the spacecraft and see where that lands in a three-dimensional view of the surface. What might we be missing? Lunar Avatar, we were also going in and potentially looking at like what's around it. Is it safely positioned? Where do we want to command it to walk to next? And doing some of that digital twinning that we had talked about. So with all that said, keep that nice and quick. Some future additions that we had planned that we would continue working on as next steps for this. Adding in some particle effects to add more complexity to the animation of those solar wind, the energetic neutral particles coming in, being able to communicate how that data is being collected. We were looking into being able to zoom out and have two different perspectives on the way the spacecraft's operating, standing next to it and interacting with it, or getting that overhead solar system view and understanding where is it in reference to the Earth, where is it in reference to other spacecraft. And again, merit mentioning that it has SPICE integrated. Another thing that we were looking forward to was importing actual SPICE data and getting trajectory information about a spacecraft to be able to position it realistically relative to where it's going in its trajectory. And multi-user collaboration. We did some GEMSEC multi-user collaboration on another project. It'd be great to do that here too and be able to have multiple people in the environment talking about what they're seeing, interacting together, describing the data, pitching ideas, whatever it may be for the stage of the mission. So in conclusion, this is the IMAP VR application that we had built, primarily initially for outreach, education, for communicating with the science team, for getting people excited about the mission. The technology that we already have built in is allowing us to visualize the spacecraft design, the instruments on the spacecraft, what the ConOps is so that you can understand the function of the mission, and then the science data that we expect to get back, even if it's currently based on a past mission. And future applications, like I just described, doing operations, doing analysis once we start getting back the real IMAP data. That's it. Thanks.
All right, we have plenty of time for questions.
A relatively small question. I'm Roger East, by the way, from College Park. Working with undergraduates on educational programs, how are you going to deliver this for educational outreach? What the Unity WebXR applications, running your own headsets. How do you expect to deliver it?
Sure, I could take that one. So we haven't really decided yet because I think Jake mentioned this, so we just did this as a sort of a demonstration for our actual science team, so across the United States as a whole. Well, actually, sorry, internationally, I guess, even because some UK folks. But yeah, we do actually want to distribute it as a release it as an actual outreach. In fact, that's something Princeton is working on right now, I think, to try to come up with a way to do that, but we're not sure. And I think we probably end up distributing some on like an app store somewhere or something, so like Steam or something like that. But probably not as it sits right now. We'd probably have to make it more maybe simplified in some way so that it would reach out to kids better because it's a little bit complex with how the spacecraft looks and everything like that. So we might make like a simplified. Plus, it also doesn't maybe like run on everyone's machine right now, especially with the HDRP being involved in there. So we probably want to simplify that a little bit with our release version. So, but yeah, we don't have any like actual plans to get it out there today, but we'd like to.
I've actually got a question myself about displaying data from multiple sensors that are collecting different types of data and collecting it at different times so that some may have more fresh data than others. Mm-hmm. Do you have thoughts on how you'd want to display the different types of data and indicate its age?
That's a good question. We definitely want to be able to show data from multiple instruments. As it sits right now, we're only able to show one instrument collecting one set of data, as you kind of saw in all the animations. It's a very early prototype of it. But yeah, if we had a full digital twin, we would want to show all the different data sources. I mean, it's kind of if I go all the way back to the very first slide, right, you kind of saw that animation right there, and where they actually have like 2 active instruments at the same time. So we're not doing that right now in the VR, but that would definitely be something. And if you look at the animation in the bottom, the very little picture in the bottom right, you can see that like it's like filling in the data from the 2 different instruments over time. And I think it's just basically overwriting whichever one is the latest, because that's probably what you want, is just get the most fresh data from whichever instrument has collected it. So
Yeah, that's a good and very challenging question. Because I know, so like we do only show one of them collecting at a time. I got to turn my head to the left when I talk. I feel like it gets way louder. We have some limited controls to be able to flip between the different energy levels measured by different instruments, so that you can you can step through energies looking at a single point in space. But that doesn't really give you that ideal of the staleness of the data. So building controls in to do things like filtering of ranges of collection periods to be able to say, give me only operations between this date and this date, and maybe doing addition or subtraction of different energy levels. There's a lot of stuff. The nice part about this is, even if we haven't solved that yet, because all of the data that you're seeing in here is dynamically read in, so we have that data to be able to live manipulate it. So as we built out more tools to be able to do that complex comparison and filtering of data, you'd be able to just immediately, as soon as the UI is built in, the data's there. So it's a hard problem to solve, but it's solvable.
So for educational purposes, how do you go about, well, for example, NVIDIA, I guess about a year ago now, showcased like a 150 terabyte visualization of data from a partnership between NASA and a retropropulsional Mars lander on surface terrain. How do you go about condensing that data from 150 terabytes to something that could like be accessible to, I guess, an educational setting?
I feel like it really depends on what the data is and what you're trying to communicate. We've definitely run up into that before, where it's like we have extremely dense point clouds of data to build a 3-dimensional model out of that is both too large for us to operate without supercomputers or on computers operating our headsets. But at the same time, you're not actually, from a human scale, getting any additional information about that. So I feel like my instinctive answer is it would really depend on what you're trying to communicate, what your data looks like, how it's possible to condense it, and just from this mode of interaction, what you're actually getting out of it. If you're really trying to get deep into data, it might be the case that you don't want to see all of it at once anyway, because you really need to focus in. But it's a challenge, for sure. We had like 800 gigabytes worth of 3D points in space that immediately crashed my application first try, so I've been there.
I think I'd add that I think an application like this would probably, if we actually used it as a science visualization tool, would probably only load a small chunk of data at once. Like it'd probably been more like open a file, right? And then I want to look at this from this instrument, and then it would know, like maybe embedded in the file, and know exactly which instrument was collected the data after the fact, and then show that. So you're not going to like try to have this one application ingest terabytes of data all at once. It's more of a tool for pulling the data off your server that contains that, right?
Probably some creative solutions to learn from video games here in terms of how to have loading in the background of stuff so that it's available by the time someone wants to see it, and creatively loading and unloading just the parts that the user is going to benefit from.
Thank you.
If there's no other questions, I do want to plug that we are demoing right after this. So if you want to put the headset on and see this, it's all available.
And when you do put the headset on and see this, and the science data potentially looks white instead of colorful, you can blame me for updating my computer and breaking the import of that data. So sorry about that.
All right, well, thank you again to all of our speakers from this session.